Okay, so let's get to it. So about today's speakers, I'm really excited about having Stuart, on today to be able to do this. Stuart, co-founder of RMS, founded in 1998. 25 years, he's an industry veteran, has a lot of knowledge, not just within motion amplification, he was a very early adopter of the technology, but just in CBM, and reliability in general. And, I don't know if you can see behind him there on the wall, it's got a pretty big fish. So, that's, that is not an optical illusion. That fish is really that big. So he is an avid fisherman. If you don't know, he's got a YouTube channel that he does that actually gets quite a few views on some of his fishing adventures. I think I think you mentioned you've got one coming up here pretty soon too. And so, and then finally I've got, he's an MA rock star. So if you've ever seen his videos, they're good. And he really knows how to use this technology, and he really knows how to make it shine. I haven't seen him since COVID, but probably the next time I get to see him in person, I probably need to get his autograph when I'm there. So anyway, you're in for a treat, but anyway, I'll let Stuart maybe, if you want to give a little background about yourself as well.
No worries. Yeah. So, like Jeff says, I've been involved with CBM reliability for the last 25 years. And for me, when I first saw the motion amplification technology, I was quite skeptical. It was one of those that almost looked too good to be true. But I used the kit on a resonance problem and visualized this lovely vacuum pump that I knew was the way it was moving. And the camera just nailed it within a few minutes. And ever since then, I've just been a real fan of the technology. It's just made my job easier. The customers love it for communication. So hopefully some of these examples we'll go through should strike home with everyone.
Cool. Yeah. And, for those of you who don't know, I kind of approached this from a little bit different path, in physics and then, started RDI to kind of get this technology out. So, I come from a little bit of different angle, but it's a lot of the same problems, and with just using cameras for solving vibration problems. So
we have a saying now, Jeff. Sorry, we have a saying now with the lads with the cameras. We say, just get the camera on it.
Yeah, that's right. Yeah, if it moves, we'll see it. Sort of thing. Yeah. Okay, well, cool. Let's go ahead and get going. So I've got a few slides on just kind of what is motion amplification. So we inevitably, there's always people who get in webinars and don't understand, what the technology is. They're new to it. So just a little bit about that. We're really using cameras to measure vibration. You can measure anywhere in the image, as you'll see through these, but once we can, use the individual pixels as displacement sensors, you can actually make the motion bigger and actually see it in the video. Normal video wouldn't capture that. And you can see anything from, lower frequency stuff, even higher frequency things too, just by using a high-speed camera. This is, I think, over 1,000. This is around 1100 hertz. So, but maybe a little bit more applicable to our industry would be something like this. Whereas, it may take an analyst a few hours to be able to see that, but to be able to figure out maybe if there's looseness there. But with the motion amplification, you're minutes in before you can get this sort of video. And we'll talk all about how, you get this kind of shot set up. But it kind of goes beyond just the typical kind of vibration, but you can also track and measure dynamic vibration as it moves through the scene. So like in this case here, where we're actually tracking something and measuring the vibration as it moves. And so you can see when it deviates from the path that it's supposed to be taking, that sort of thing. But, we're really, again, we're leveraging the camera to measure things that aren't visible by the eye. The idea is, what once was maybe the story had to be told by that spectrum that you're seeing, now can be told by a video. And that story is not necessarily communicating to maybe someone who's not technical, but it's really the understanding for the technician themselves or the analyst themselves, because the amount of information that you get back is really unparalleled with a camera. And so now you can visualize this and quantify and understand not just the vibration, but the context of the vibration. It sort of turns things on its head, as you'll see. You know, and in terms of scalability too, if you start to think about a camera, a pixel being a sensor, right? So you think of it being just a displacement sensor. Now you're talking about 1, 2, 10, 100, a million, 2 million data points that you're measuring simultaneously. So, you can scale up data collection and do what we call full field vibration, where you're measuring everything across the field of view. And so it gets pretty interesting when you can do that. You start to learn a lot more things and see new things that you've never seen before. And we'll sort of get to that a little bit too. For those of you who are wondering about maybe it's the technical specifications, you can kind of read that. I'll highlight a few of these things, but fundamentally we're measuring displacement. We can do this live, which we'll demonstrate. We'll kind of talk through, Stuart will talk through these examples, and we'll talk about them and also kind of supplement that with some demonstration of the software. But you can see down to small motions that 0.01 mils or less than a micron, and see amplify up to 500 times. And what's interesting too is it goes beyond just the typical vibration single point reading, which we can do anywhere in the scene, but you can also do things like measure shaft displacement because it's non-contact, or measure torsional with these new features that we've developed with the camera. So finally, the last slide in the intro I just want to show here is just kind of the picture of what we're looking at. You can do this anywhere from a point-in-time troubleshooting, which you see on the left, the Iris-M. You can supplement that with high-speed camera if you need to capture faster events. You can move to an MX camera, or you can do continuous monitoring with the Iris-CM. So you have this variety of options that you can kind of expand across with troubleshooting to continuous monitoring, just depending on what problem you're trying to solve. So with that, we'll go ahead and we'll jump straight into the case studies and start talking about motion amplification.
Yeah. So yeah, if you just want to play this one, Jeff, and we'll have a chat about it. So this is a pump, had a high one times on the pump, and we knew it was sort of in a resonance problem, but we wanted to sort of visualize the machine. And what I want to get across here to people that maybe use the technology is basically moving around the asset really, and actually documenting the different parts of the machine. So don't just sit in one place with a tripod, because it's not like a vibration analyzer that's got a route built in saying go to this point, go to that point. It's down to you where you go. And what I would say is document the whole machine. And as you can see here, we're focusing in on the feet of the pump, and we see two things there: the bed's flexing, but also it looks like there's a loose bolt on the rear of the pump. So then what we'll do, we'll probably change lens, put a 25mm lens on, and actually get a little bit closer. And here we are, we're looking at the foot now. But unbelievably, you can actually see there's a little crack there that the camera's highlighted. And when we was on this machine, I had the engineer with me, and I'm saying there's a crack there, and he's like scraping away the dirt, is there? And yeah, the camera's just brilliant for that. So these little subtleties, you've got to get in there. And these are some of, it's not the best pump base, this one, is it? But we're getting around the back of the machine now, and we're documenting each foot. And you can see, even though you think something's tight or bolted down, the camera's clearly showing that one's obviously loose. Very poor base on that one, needs a lot of work. So the theme with that was sort of move around the asset. That's the point I'm trying to get across, because I know a lot of people, we do a lot of training with the camera, and everyone seems to like get concreted to one spot, and you've got to move with this camera.
I always think sometimes it's like teaching people to dance, and when you're there, like they don't want to pick their feet up, they want to kind of sway their body, but you got to get them, moving their feet and moving around. It's kind of a similar approach. You shot this one pretty early, right? I mean, this was one of the early shots that you guys did.
Do you know what, Jeff? I think this was me and Keith's first one. We really we lit it up, and we got in there. And it was just a great example to start with. And yeah, you can see the bass as well. It's just flexing it needs totally new bass and some extra supports to change the natural frequency of the pipework. And
you know, when I first saw this video, one of the things that I took away from it is like a couple of things, but one of the things that I thought is really interesting about this is how, you know, the first shot, you know, you took that shot, which I think is really important, and you really emphasize that, taking that holistic shot where you see everything, right? And it's almost like the asset itself, you know, if you look at the video, because, you know, you can analyze this in the field and you can look right there. It sort of guided you to the spot because you could see the motion, and it really led you to the next spot that you needed to take. And I think that happens a lot if people just survey the data.
Yeah, it's so important when you do the shot to make sure you've got the bottom of the concrete bedding, the feet. If you sort of miss a connection, you might be missing an actual problem. So
yeah, because a shot like this, and this is one of the things that I always want people to remember, is that, you know, when you're out there, you're set up, you're collecting the data, you know, it literally takes you 5 extra seconds to take that extra wide angle shot, you know, and it's not really one that you want to miss. The other thing that too about this data set that I think is really interesting is the idea on with motion amplification. I think people need to remember is, you know, all the way from big to small, you can see this big, you know, sort of view, but really down to the crack level where it's just a single pixel. You're not, you know, because the cameras, you know, have those sensors that are butted up right up against each other. You're getting that continuous coverage. And if a crack is even a pixel wide, the camera's still going to pick it up.
Yeah. They almost flash, don't they? The crack, because of the light. It's really, really good.
Yeah. Like there it is. You know, you can actually see that. And that's about a pixel wide, you know, and it's, but no stone gets unturned, you know, left unturned, you know, with the camera because of that. So
cool. Yeah, we'll go on to the next one, Jeff. We'll have a look. So the next one, I think I get often asked, how do we know when to get the camera out? And this is a classic example. It's a cleaning, it's a sugar plant, it's a shaker screen, and it cleans the sugar beet, washes the dirt off the product. And is that playing, Jeff? Oh yeah.
Yeah, I move anytime I move the chat up, it pauses the video. So yeah.
So this motor on top, this is the trend, the overall trend, which went up to 50 millimeters per second, that prompted really to get the camera out. So once we've got this high, could you jump it back, Jeff? Sorry.
Yeah, and just real quick, I got to ask you, when you see things like this, just out of curiosity, because it happens to me, do you still get like this look of kind of like, that's crazy?
Yeah, it's really, we get all giddy. We get all giddy when we see, look at that, look at those struts. And yeah, we're doing this job with Keith, actually, and he spotted those, says they don't look right. But
you want me to go back to the beginning? Or?
Yeah, to the trend. Yeah, to the trend, yeah. Yeah, so it's about incorporating your routine VA routes, and this was a great one. You can see we've got a slightly erratic trend, that's what it does, but then it jumped up and it's like, right, the frequency was at the frequency of the screen. So we got the camera, we're 25 meters away here. We're getting a real wide shot and we're looking for anything out of the ordinary. And yeah, there's quite a lot of movement, and those vertical struts, you can see some at the front there, rock steady. So we were not happy with those at all. And then it started moving to the motion again, getting in there, getting closer. There's another shot just at the connection.
Wow.
And you sort of see the vertical strut just on that left-hand side. There's a lot of motion there. And this is a filtered video. So what we do, we get the frequency of the screen. I think it's something about 800 CPM, I think, something like that. So these are the struts looking there. And although there's a lot of product, chopped bits of sugar beet, I can see there's severe movement on these. So I didn't even need to get a spade and start digging these out. I knew that these struts had failed. So what we did, the guys, they got in there while it was still running, did a bit of a temporary repair. added a bit of a brace, and as you can see there, the after shot and the levels have come right back down to 12, which for this machine is acceptable. So
I'll start that one over, yeah, just so they can see the before, yeah.
So in this I mean, this is a complicated structure. There's little beams everywhere, and trying to go around with a sensor to suss what's happening, it's impossible. But you get the camera and you're there 5 minutes and you boom, look at those struts, and they're even behind a safety guard as well, like, to be fair. So
yeah, it's interesting because in situations like this, I think that it's a hard problem to tackle, and it's kind of like, what sensors do you use? And I think it's a good point, in these complex fields, it's still, and we'll talk about this in the next one, but there's other techniques like, pulling up a motion map, that you can use to highlight these areas. But in terms of kind of setup for this, again, I think, it's really important to remember too, that these complex fields can pretty easily be handled with the camera because, it's really getting everything in the field of view.
Yeah, I think the point is, and you mentioned it earlier, every pixel on that screen is a sensor. So every last little, even look at the sugar beet down in the bottom, it's motion amplifying the product because it's been moved by the actual strut. And yeah, it's just great. I remember one Keith had actually, my colleague Keith, he had a big crushing mill and it was covered in dust, but he shot the dust and the dust was moving, and you could tell there was probably a crack underneath a foot. So yeah, you don't miss a trick with the camera.
So we had a question. I'm gonna let this video play again. We'll get to a question. It says, how can we differentiate between sources of 1x high vibration using the motion amplification camera? It's a good question. Mm-hmm. So you get a high 1x, right? And so how do you differentiate between that?
So with the with the high 1 times, what we'd do, we'd filter into that actual frequency, so eliminate everything else, and then we're looking at the motion. Really, if it's on a fan, is it sort of an unbalanced motion? Have we got a loose bed? Have we got a flexibility in the bed? We may have to look for possible resonance problems and do some extra tests with the camera. But my first port of call is really with the 1 times. I can honestly say, I would say 80% of the 1 times problems I see across industry is down to poor bases. And that might be a looseness, a flexibility, or a resonance problem. There isn't that many now where it's an unbalance or misalignment. Most places are doing good alignment, balancing fans. It's bases, and a lot of modern bases are manufactured quite cheaply, so the materials used are a lot thinner. There's a massive drive for people to go variable speed drives, and it just creates a whole host of problems because you've got a bed that's very weak to start with, put a VSD on it, ramp it through its speed range, and suddenly you're going to hit a resonance. So these are all at 1 times. So yeah.
I was going to say, often, if you're trying to be able to see, I think lots of times, and that's a good point to make with the camera. Lots of times I think we have this, it's kind of a paradigm shift of the way you do thinking. Like we're kind of taught, well, you see a peak, and it's a high 1 times, but with the camera, you can actually literally see what it is. I mean, you just see the foot lifting up off the ground, and you can confirm what it is. You can see the looseness. You can see what's contributing to that motion. So that's where you can figure out, what the cause is.
Yeah, I mean, if it's the forces there, say a 1 times, and it is an unbalance or alignment, what you tend to see on the video is almost like the machine wanting to rip itself off the bed. You actually see the force, the vibration, and there won't be a looseness there, but you'll actually see the metal flexing and deforming, which is quite amazing. And I think towards the end, Jeff, haven't we got a good, amazing shot actually of something like that.
We'll jump to the next one. Yeah. I really like this one. It's a very good example.
Yeah. So this was a good one. We had client basically said they felt it's a brand new machine, steam turbine, HPLP at each end, and they felt that there was some pipework vibration on the lube oil. And you can see this little center section here, and this is what they felt, and they weren't sure, is it, we don't feel it's right. But they just thought it was there. So what we did, again, you've got to go wide, scan the whole area, and we suddenly found it wasn't just in that area. It was all the way through the turbine onto each end, the HP and LP. And then what we do, we apply some criteria, the Energy Institute guidelines, just as a scanning, and we can actually put a level against the frequency and see if it's in concern. This was in concern. We then did some bump tests, just using traditional analyzer, and sure enough, we got some excitation, natural frequencies very close to the generator speed, 25 hertz. Now this, Jeff, this was absolutely key on this job. This is adding some bracing later on. This is in live mode. And Keith there, he's got a temporary brace, and he's tightening it up. So if we just play that one back, Jeff, and you'll see the vibration just die. So imagine I'm on this job and I'm saying, Keith, tighten it up, and he does that, and then boom, we've killed it. We've changed the natural frequency. And it's like having another sense. You feel like Superman when you've got that, because sometimes when you stiffen it, you might put it somewhere else, and we could see there we had it. We'd literally got it in the perfect spot. So it did need quite a few braces in different parts, and here's some before and after shots. But we really reduced the vibration levels down massively. And what's great with the camera, when you motion amplify, if the vibration levels are low in the image, it's not moving as much like that. That is still amplified, but the vibration's dropped. So you don't see it. So that's a key thing for me, that what's great with the camera, because it's very difficult to make a good machine look bad with the camera, sort of whacking the levels up. Here we go, down to 0.7 of a millimeter per second now on these bits of
quite a bit difference, right?
Yeah. And it's great, this Energy Institute for scanning for vibrations. It's looking at, like, they've done a lot of research with like cyclic fatigue failures on pipework, and great as that initial stab of looking at it. So for me, live mode there was the real game changer for doing that, because we could assess it there and then. Worked really well.
Yeah. So speaking of which, why don't I show, I'll pull up the software and I'll just show where that is, kind of do a short little demonstration of that. Yeah. So let's see, I've got a little rotor kit here. It's on a smart switch, so I can actually turn that on with my phone.
Pipework, the live was a big game changer for us. You could scan lots of areas quickly.
So it's fairly easy to do. I mean, that's one of the things I think everybody should take advantage of when they're using the camera, because the amount, how quick it is to be able to do scans. So you set the camera up, you've got it here, you're a few minutes into kind of setting it up and turning it on and everything. But it's a click of a button. So if you press this button up here, the live, it goes straight into live, and you can increase or decrease your amplification, but that's it. And so Stuart was mentioning, they were watching this live. Just imagine, you put a brace on that and you brace it, and then the vibration levels go down. And if you do want to measure it live, kind of like they were mentioning, you can do that too. So if you pull up this and you draw a box, and I just clicked on this little measurement icon, and you can get that get that waveform. So that's how you can see sort of in real time, what's happening with the asset. Really just pretty simple to do.
Yeah, it's a great tool. We use it a lot for pipe work, but to be fair, if I go to, say I'm scanning a pump, it's just there now. I'll have a quick look live mode, put up the amplification, let's see what I'm dealing with, what's the problem. Really.
I like to turn this on immediately too, because it's just, there's really no extra time added. You put it on, and you can see it and kind of come up with a game plan to see what's moving. And also it's really quick to, determine, is there any piping or anything around the area that's moving, because I know a lot of people who've just picked up, conduit and things that are loose that really should just be done and taken care of. And nobody's really monitoring that stuff.
Yeah, it's a lot of the time, it's not just say the motor or the pump, it's the instrumentation that's hanging off that might have an issue. We've certainly found a few problems with that. But commissioning a new plant and you scanning work areas, really cool. The icon next to it, I don't know what you'd call that, Jeff. Is that the restart one? I often, if I'm...
this one here, yeah, kind of return to live. So if you slow it down, of course, kind of like a slow speed, it keeps taking data, but you've slowed it down. So you're playing it back a tenth of the speed. You sort of go back in time, so to speak, by a factor of 10. And you can always press this to get it to kind of go to the current time. Yeah, it's just it's instantaneous. So if I just move the camera, I'm scanning there, just click that right-hand button, just instantly I'm back instantly live again. So I'll turn this off. And we can kind of watch it go through its little coast down there. Yeah. So, okay, cool. Yeah, that's that's good. And I think something anybody should be picking up if they want to, when their camera. I always think that you should be using the live mode for sure. Something relevant to what you just did. They said, if I understand correctly, motion amplification is synonymous with ODS for bump testing. Do you still need a vibe analyzer with impact and hammer in response with the accelerometer? No, I mean, we've had some, I think we've got one at the end of this. We've had some fantastic results with the camera and doing bump tests. And we did some comparisons using a tuned hammer, force hammer. And yeah, it was really good. We got some great data, and I think I've got an example at the end where we do some bump testing. So yeah, I think everybody can remember that you can get full vibration spectrum and waveforms out of it, so you can actually see that. And we'll show that. Yeah, seeing the full picture with it. That's the thing again, and I won't spoil it, but the one at the end is all about when we bumped it. Right, I can see what's actually moving here. Yeah. Okay, we'll jump to the next one then. Yeah, this is I'm a big fan of this case study. Yeah, as you know. Yeah, so. This was an early one we had, and it was another light bulb moment of wow, this technology is something special. And we had a pump. This is on one of our regular jobs, and there's a whole pump alley of these pumps, all similar. And we had a high 2 times on it. When I say high, it's not ridiculous. I think at times it went up to sort of 5 millimeters per second. But bear in mind, all the other pumps were like 1 millimeter per second, showing quite high axial as well. And often with that, we're thinking, let's check alignment, let's check all the holding down bolts. And that's what the guys did. Good set of lads, knew what they're doing. They did it twice over 6 months. We asked them twice, and every time we can't find anything. The alignment's good. Everything's tight. So we got the camera on it. We just sort of quite recently got the camera. And it is subtle this a bit. This is amplified now. Can you see the motor just rocking front to back sort of vertically? Very subtly, but it's there. You can just see the motion. It's not an excessive movement, but it's there. You can see the movement. And I'm looking at these videos going, I don't get it. And then the moment when we put the camera under the rear of the motor and film the actual plate that's attached to another plate, and you could see it was sort of bent and flexing like a banana. And that was why nobody could find it, because you check those bolts, they're going to be tight, but it's the plate. That's the steel plate that's the problem. And go ahead, sir. It's just causing a rocking motion on the pump. And it's subtle. Yeah. Yeah. But how long did that take? I think we'd done a few external shots, and I think within 10 minutes we'd found that.
and they'd been on it twice for 6 months. And we were,
you know, and what I liked about this, and I'll kind of play some of this back here, you know, just with where they find it, is when you get in here again, you know, because the camera can do down to pixel level, you know, it is so easy to miss that if you didn't have that level of granularity, and then also, you know, the fact that you can just put that camera right underneath, you know, it allows you to go places and see things that really you couldn't see before. And what in terms of approach and setting things up, I really encourage people to move, you know, the camera to be able to get a really good look at it. Also, I would say that if you notice in a lot of Stuart shots, it's kind of like a Where's Waldo. You can always find one of his lights in there where he's kind of spotted it really nicely. And again, you know, real easy to set. You know, you can get these lights. You know, we sell them. There's lots of, you know, off the shelf ones that are, you know, magnetic and can kind of really easily placed into kind of darker areas like this and easily get that shot. So that's one of the takeaways that I really encourage people from this, is just have that flexibility and use that camera in places that you normally wouldn't traditionally be able to take measurements. Yeah.
It's where the connections are. I'm always looking where where it's bolted to, and even concrete. Don't discount a giant 5-ton concrete base, because we've seen those moving as well. Yeah. When you think there's no way that it would happen. Yeah. Okay, so we'll move on to the next one here. Yeah, another beauty with a camera is flexibility. You can use it for transient problems, so really like stuff that's not happening all the time. And this is a robot, and basically what had happened, they were getting lots of failures, structural failures on the robot, cracks, linear bearing failures. And it all occurred after they added an extra station, this station 2. And if we just start the video again, Jeff.
Oh, it's playing right now. Is it not playing for you?
Yeah, no, sorry. I just want to start back a bit for the.
Oh, back a bit. Yeah, sure. Yeah.
Sorry.
Right there? Yeah, right before that cycle.
Yeah. Yeah, before it hits station 2.
Yeah.
A bit more to the left, Jeff. Yeah. There we go. So you can see this is a 2-minute acquisition, and we're about to hit station 2. And you can see the vibration on the time waveform, and the actual robot really shook then when it lifted the load. So we then focused in on that station 2 move, and you can see the base, it's all moving, and there was a frequency there of 3.6 hertz, quite low. Here's another angle, station 2 move, lift. Ooh, that is all over the shop. Again, you don't need to be a genius. You look at that and say, there's a 1/4 ton of weight that robot's lifting. That base is just not up to the job, basically. They've added some stiffness there, but really, they're just flexing. They're just bending. The feet, what it really needs is like basically a concrete bed, and proper bolting down. And that will reduce some of the stress on the actual robot arm and that. So again, you can see we're doing different angles, and we're seeing these little, they've added the struts, and you can see them, they're just flexing.
Yeah.
You can't see that with your eye. You cannot see that with your eye. So
yeah, you know, and you know, I like this shot here again, just kind of coming back to that, you know, it's so easy to connect the dots, right? You've got the station, you've got the base, and you have the context of what's happening, right? You know, whereas, you know, you might not have this, you might not think to look there, but you know, and it's high, you know, you've got a region drawn here, right? But you have to see the video to see that motion, say, hey, that's where I need to be looking. It's not as if you go into it thinking like, I know this base is going to be flexing, right?
Yeah. I mean, you can see the ring down on the waveform there. Is it got excited and just down, and the whole robot flexes like so. And the thing with these shots, you really need to drop your because it's low frequency. There's no need to shoot at 100 frames per second, something like this. I mean, what have I got there? Is it 25 hertz maybe?
Yeah, it looks around 25. So you've collected like 50 frames per second.
but to be fair, we could probably go even lower than that and just reduce the file size a bit. But like I said, the whole cycle was 2 minutes. So it's a 2-minute acquisition, where a lot of the time on a pump or rotating kit, we're probably doing 3-5 seconds. So
yeah, I mean, it's a good point, because we get a lot of people that look at kilns or slow moving stuff and don't, you know, it's a good takeaway from this to don't be hesitant to drop your frame rate, because if you don't need to see above 30 hertz, you don't need to collect the data. There's no real reason to do it.
No, exactly. Yeah. It just makes the data more manageable as well, and everything's
sure. So someone says, could we record the motion amplification of the pump while coast down and assess the critical speeds and resonance? Absolutely, right?
Yeah,
totally do that.
Yeah. What's nice as well when you do that and you do a rundown or coast down and you draw an ROI, a region of interest, and get a spectrum, it's a bit like peak hold. So it holds it across that range. So you literally end up with a graph that pretty much shows you where the highest vibration was at what frequency. So but also if you wanted to pull in the waveform and select a region and just have a spectrum of that, you can do that as well, can't you? But you'll need so many samples to do that. But yeah, that's possible.
Yeah, and you get the full field during that coast down. You see, you don't have to pick and choose.
Yeah.
Okay, so let's hit this other one.
So yeah, this is quite a recent one, very interesting. This is a conveyor drive. It's got big conveyor belt. It's got 2 drives. One on the left, not a problem. You can see it's not moving on this video. One on the right, they had lots of issues, cracking on the base, literally lots of problems. So we actually shot this. This is the video. We can see some significant movement. And I actually found a cracked weld. And amazingly, the guys got it welded while I was there. This is after it's been welded. We can see the motors dipping down on the right-hand side. These motion vectors are great. You can see this is almost like, it's like the phase angle, really. What's the phase angle? We can see it. This is the left side. Real heavy motion. It's doing about 20 millimeters per second. This we can see the RSJ flexing a bit here. So like we've done before, we're moving round and we're assessing what's this base like. Is it bolted down good to start with?
See the amplitude change too with those vectors across that.
Yes,
base.
yeah, that bend in the middle there, and just the force here is flexing.
Wow.
And it's pretty thing. Now, if we look at that bolt, this isn't the big issue, but it is an issue. You can see just some looseness there. So I think the force of this motor at one time is literally sort of pulled that bolt up. So that needed addressing. But you can see on the far side now, we're around the other side, we're going to move in and we're going to look where this motion is. And we can see the main RSJ is pretty good. But when we get close up now to this front foot, this is where the welds have been going. You can see why they've been going and they're going to go again. Because that
crack
of this base. Okay. So they checked the alignment, they'd had 2 or 3 motors on there and they're still getting this vibration. So the next thing I did, I think, is it the next slide, Jeff?
Yeah.
Yeah. I just had my analyzer with me, so I could have done it with the camera, but I was on my own. I was just rushing, trying to get as much data as possible. I did a quick coast down, and sure enough, as the power was shut off, it runs at 1495. It got to 1460 and the vibration rocketed. You can see there. So straight away, I'm thinking, right, I think we might be looking at a resonance problem here, excitation. So I've then got in my head at 1460, this is getting excited. So the next thing, I think the next shot, this is where the camera really comes in. So I could have done with a lot bigger hammer, 2-ton motor, but this is how good the camera is.
Yeah, got it, didn't it? Yeah.
Yeah, so I've filtered the video to 1462. I've whacked the amplification up. That's why the quality's a bit grainy, but you can see that whole motor rocking in the same manner that we saw when it was running. So this is off now, totally off.
Yeah.
And I knew then, right, we've got a resonance problem. So what I did, I haven't got it here, I bump tested the other motor and I got 1100 CPM, and it felt a lot heavier, dead, felt a different beast. So we're looking into it at the minute, and what we think, this is an old motor that's been sort of redesigned, and I'm thinking, is the other one a cast one that's a lot heavier, and this one's a lighter motor. So what we're going to do, it's not easy just to get these off and weigh them because they're in production. So I've said, let's add 300 kilo of mass. We did some calculations. We're going to add it to this motor, and we're going to see what the vibration levels do. And because we know that natural frequency is around 1460, adding the mass will lower it. And as we push it away from the running speed of 1495, I'm expecting that to come down from 20 significant. I'd like to see it down to less than 5, to be fair. If that works successfully, they're doing it right now, to be fair. This is a real live one. If that works, great. If not, we might go the other way and actually look at the bass, improve it, stiffen it, and send the 1460 natural frequency way above the 1495 and do it that way. Because if it needs 500 kilo, I don't think it will, but if it did, it starts getting impractical to add that amount of mass on this machine. So that'll dictate which way we go on this example. But for me, it was great to do that bump test with a camera. I saw the whole thing rock, because you are thinking what's in resonance here, what part. And when I got confidence, was like, right, I know what it is now. So, yeah. But we could have done the rundown as well with the camera. We could have done that. I just had my analyzer did it. But,
yeah, makes sense. Cool. Let's get to. Is this this is the same one, right?
A hammer, don't I, Jeff? I think it's got me big. I need a bigger hammer.
Yeah, you're gonna have to.
It's got me big rubber hammer. It's like one of these paving slab things, because you're trying to excite something weighing over 2 tons. It's crazy. This
one's an interesting one because we get a lot of questions about daylight. I mean, it's a totally different animal collecting data with the camera, as opposed to being inside a facility, as opposed to being outside a facility.
Yeah. So this is a great example. Customer asked us to assess quite a large structure. It's a chemical plant. They knew the structures vibrated a bit, and they wanted to assess in which direction. They were looking at structural loading. And if we go back to the original shot, Jeff, this is a lot for MA users, really. Because the camera uses light, you really got to understand where it works best. And this was a real hot day. Was in the afternoon. This is the raw data, and you can see we've got a lot of shadows. Because the camera can sort of see the heat, the change in light, sort of see heat. So for me, that is the worst time to do this type of job. So what I did, I said to the customer, I said, look, I'll pencil in next week, and I'm going to look for a cloudy day. I'm going to come early morning when the temperature's not heated up all the tarmac. And this different world. Look at these shots now. The more
it's a very good tip. Yeah, for sure. Yeah.
So if we play this one, if we look at I think the structure at the back. Sorry, the next video, Jeff.
Next one. Yeah.
So that was the sunny day where it wasn't great. So this next shot, is it playing all right?
Yep, it's playing now.
Yeah, it's just a bit of a delay. That's the raw data, 0 to 12 hertz. Again, I'm shooting low frequency. Structures often are very low. This is 1.44 hertz filtered to it. Look at the big tower at the back. You can see it rocking. We can do a measure and get a feel. 1.44 hertz, which has actually been excited by an agitator. So what we can also do, filter to some different frequencies. This is still the 1.44 hertz. Look at that.
Yeah.
Rocking.
Look at that.
whole structure. And this is a big structure.
Yeah.
It's amazing. With a camera, you can see these type of things, but it's all about knowing, getting that frequency.
Look at that piping, just
yeah. So this is
moving all over the place
hertz now. So this is more like process excitation of the pipe work, different frequency. We've removed the 1.4 and I've filtered a bit of a band, 3 to 6. And we were just assessing these cooler pipes really. So that's what I love about the camera as well. You can just tune into different frequencies. And while I was doing this job, I actually found a couple of little safety concerns. Here was the pipe. I could tell just off the video there was it was excessive. It needed supporting. And I think I'm 80 meters away with a 25.
80 meters away here. Yeah.
Yeah, that shot. Yeah.
Yeah.
Yeah, definitely. Yeah.
Yeah. Zoom in with the lens. You know, I think one of these things, I guess, just to point out to people with collecting this is just, again, the granularity of that you can get with these individual pipes, you know, and being able to get down and see them.
I mean, that is a complicated structure with pipe work everywhere. Could you imagine trying to go around with an accelerometer trying to assess all that pipe work? In fact, you wouldn't even get to some of it because it's
it is probably not possible.
4 stories up into it. So yeah, it's absolutely game changing on stuff like that. Oh, this is a good one. This one, isn't it?
I agree. I really do like this one.
So this is hot off the press. This and Jeff and the guys at RDI have developed this amazing. It's hard to get your head around it. We're still getting his head around it, and it's a tack sync. So what we're doing is we're putting a piece of reflective tape on a rotating component on a shaft, and we're syncing the camera to take a shot every revolution. Boom, boom. That the camera's firing off, and we'll take how many cycles, shots, Jeff? Maybe 500.
Yeah, 4. I think 4 to 800 is something I usually collect it. Yeah.
Yeah. So what you get is this result. You'll see it in a minute. This resultant video where the shaft has actually been frozen. Okay. So you don't see it rotating. It's now frozen. It a bit like a strobe type effect. But then this is the thing that just blows my mind. We can then motion amplify the shaft. Okay. But Jeff, do you just want to explain, because you'll explain it a lot better than me, of what we're actually doing there in terms of like removing the 1x component?
Yeah, so it really does with synchronous. It removes the synchronous speed, and what's left is all the non-synchronous. So now you don't have the rotation get in the way, and you can actually visualize the shaft just like a vibrating object. And the results are pretty interesting. You know, for me, one of the interesting things about this is being able to see things that you've never seen before. You know, just a whole new set of applications.
Yeah, I mean, I've seen things in the spectrums of my traditional vibration data that they ain't on no wall chart, they ain't on any training, but they're in there and you think, what is that? What are those sidebands? And this is a great example. So it's a dyno, this is a testing dyno, and they were having lots of problems with these bearings on here. You can see there's a flywheel and a couple of bearings. And we did traditional vibration analysis with this analyzer, and you can see some of the plots there. And at first, it just looks like, oh, a rotating looseness problem. I've got a set of harmonics. But to be fair, the G levels are quite low, so there's not a lot of impacting. Anyway, when we went deeper into it, it was more that there was a flexibility in these bearings, basically, which are generating these harmonics up to sort of 4 or 5 times. So it's not like an actual loose part that's impacting. It's actually a cocked bearing and it's been distorted. But what was amazing, and this, we're still trying to get his head around it. If you look at the spectrum on the bottom left, we only saw it in the data. We could do with a higher resolution plot here, but you'll notice there is some sidebands around these peaks, more to one side actually. And these were at 4.1 hertz. Okay, so this is rotating at 2000 RPM. What's that in hertz, Jeff?
I don't know. 2000.
30
get my calculator. 30, yeah, a little over 30. Yeah.
Yeah. Okay. So we have got a very low frequency on these sidebands. really puzzled. Part of the process of what we're doing, we thought, let's try this taxing technology on it. So we put some tape on, and then if we go to the next shot, this is just unbelievable. So this is in the program, and you take a video using the taxing, and then you draw your little red box anywhere you want, and you can get a spectrum. And sure enough, out pops 4.1 hertz, and we're like, ooh, that is pretty interesting. And at this point, we're getting quite excited, thinking, what's this going to play like? So we filter to this frequency, and we use another technique in the software called HDR, which is absolutely awesome. High density recording, really super smooth motion. So I think the next shot we'll have a look at what this was doing. So bear in mind, this is doing 2000 RPM.
Yeah, it's turning right now.
That's turning. I'll just go back to the start again, Jeff, on that one. You can actually see the shaft flexing, the flywheel, there's some axial motion. And this is close up of the drive end bearing. This shaft on the left's doing 2000 RPM, but it's frozen. Unbelievable. So we think it's a reaction to the poor bearing design that's sort of allowing the shaft to do this motion.
Yeah, it's bending there. You can see it just, you know.
And it's thrusting into those bearings. Yeah. That's why these bearings aren't lasting very long. Another shot we did at the back, it was with the taxing, but it just happened to be, and I could see also there was a bit of looseness. One of the sleeves was loose on the shaft. Again, this end is doing 2000 RPM, but it's frozen. It's just mind-boggling to see it. So for us, this taxing, it's early days, but we're starting to see some really interesting things that we'd never really see, and you'd even think. It's in the data though, isn't it? It's in the standard data, but it's subtle. It's subtly in there. So I think you'll see sort of torsional things on that, and shaft criticals is another one you might see, and so flexing.
New sort of bearing defect, kind of ways to look at bearing defects. And again, for this setup, it's a little bit more complicated, and I'll go into it in advanced feature, but really you use the tack tape and you get the laser tack, similar to how you would put a tack on it now.
Yeah. I mean, you do, there's no doubt it's a bit more intensive on the job. You've got to get permission to take guards off and see things rotating. But when you've got a serious issue like that, it's not, often you put a few safety measures in place, you can get the guards off and you can get looking at this stuff. Which is going to get you down to the root cause. So this next one, we think is a bit of a world first, this one. So this is on another dyno next to it, and we got slightly different. We've still got the harmonics, but we got a frequency there. It's at 4.08 orders. And this is actually the outer race frequency, the ball pass frequency outer race. Now, it's very unusual because it's the first harmonic, okay? I haven't got the time waveform on there, but it was very low Gs, so it was not impacting a lot. It wasn't like I've got a spalled bearing here with massive potholes. It wasn't noisy. There was a vibration at the outer race frequency, first harmonic. I've seen it a couple of times, but it's quite rare. So whenever people think you've always got to use like enveloping, or it's always in Gs. Not always. You can see some of these bearing faults in velocity. So this was well within the range of the camera. I think I used the MX on this. I think it's 128 hertz. So that's every second, 128 balls are passing a point on that machine. So it was just crying out to be visualized with the camera. So let's have a look at it. And I'm still trying to get my head around this one when we see it. So this is filtered to that 128 hertz. Look at the bearing. It's almost squashing up and down like a tennis ball. It's really flexing. Unbelievable.
Yeah, it really is.
That's a bearing frequency we're looking at. So the guys there, they're pulling the bearing out, and we're going to check for two things. I think it's related to the problem on this machine where they're having bearing problems, and I think the distortion of the bearing is causing the vibration at the outer race ball pass frequency. That's why it's the first harmonic. Now, it may be that there's some wear in there, but it's really even without any potholes impacting. So we're going to inspect the bearing and have a look, but I'm no doubt it's to do with basically a weak bearing design on a real heavy flywheel doing 2000 RPM, just not up to these bearings, I think. But to see it is, that's crazy stuff.
So that's our last case study. I want to just really quickly, we're right at time. So I wanted to really quickly, mention, before we end that, we're going to do another one of these. It's going to be next week. I'll be on to go over advanced features. You heard Stuart talk about the TAC. We mentioned motion map. We mentioned filtering. We have a question that says, how do you filter? How do you pick what frequency to filter for? There's a technique called motion map that we'll be going into that will show you can measure anywhere. We'll show those sorts of things, but we'll go in through and talk about displacement, time waveform, stabilization, how to do annotation. This whole list of shaft inspection and speed detection and phase. We'll have all these available to talk about in the next webinar. Here's the HDR that Stuart talked about, the live motion amplification. So lots of features in there that we'll be going through, and and I'm happy to talk about those as the questions come in as well, sort of a on demand sort of thing, really informal. So anyway, I want to hit on that, and I think we answered most of the questions. We had a lot of questions. We answered a lot of them along the way. But what I would say too is that we will also get back with everybody. If we didn't have a chance to answer your questions, we'll get back with you. We have your contact information. We can get to you directly on those questions. So if we didn't get to your question, we will be reaching out to answer those. The last thing I want to point out too is that Stuart's contact information is here. So if you want to reach out to Stuart directly, their YouTube page is great if you want to kind of check out the videos. And then our YouTube page as well, and contact information for myself. We like talking about this, so we'd be happy to discuss if you have any other questions. So with that, I want to thank Stuart for joining us on this webinar, and thank everybody for taking the time out. We know time's valuable, so we really appreciate it.